So this presentation will focus on realizing ORM, meaning an ORM model, with the JavaScript fact engine, which is the technology I've developed. In many ways, in the ORM community has focused a long time on developing databases with ORM, but there's a lot more that we can do with an ORM model. The database is really just the tip of the iceberg when you're dealing with development costs and how much code is required to put an application together. So this is looking at how to put a full data stack and together using an ORM model, and using that as a lot more than a pretty picture on the wall, right? Really is the central development artifact to coordinate all of the different implementation layers and get a really smooth data integration. So before jumping into the actual stack of software, I'd like to just take a moment to talk about where this started and why I'm doing this. The JFE engine originally started as a way to display ORM diagrams in the browser and also edit them in that environment. Diagram editing is a fairly difficult thing because it has to be very responsive, right? You don't have time to go back to a server and say, oh, could you do my line routing for me, right? When you drag a shape, the lines have to move immediately. You can also do an awful lot of changes that need to be finished before they're consistent. In other words, you're staying a long time in a editing environment on the browser before you actually send data back and forth to the server. So I needed to be able to track state changes, do normal editing operations, undo, redo, do incremental validation, do responsive validation within the system. And that state change then had to be serializable, sent to the server, and I also had to be able to get state changes from the server and essentially rebase the system. All incremental, right? You don't want to send an entire model, which can be massive amounts of data back and forth every time you're doing a small edit. So the system also, I really wanted to be fact-based. I am dealing with object role modeling, which is a fact-based system, right? But for me, fact-based means several things, right? Basically, you're making a statement and say make it true. So if you say this object exists, you don't care if you're creating it initially or if it's already there and you just get it back. This compares to a database system where if you create the same object a second time, it throws, right? So often I didn't know with the system that the data I was getting back came in any particular order. So you had to be able to repeat facts, you had to be able to reorder the statements and get the same output from the system. And obviously I wanted a system that worked well with ORM, right? That's my primary tool development. So eventually I want to be able to bootstrap an ORM tool with ORM itself and move that into a central role in the development of the tool. So as you can see from this picture, there are a lot of moving pieces in this application, but there's not a lot of blue. Blue here means custom code, which is handwritten code. So you write your UI, you write a basic routing engine on the back end to get requests from the UI to the application. You're still writing the application, right? But the vast majority of work required to get data from the system, translate it into the database, both import and read, so translating back out, right? Get the query, get back into data you can use on your front end is all generated for you by the ORM model, right? Norma Pro generates this. The ORM web tool that we'll show later also generates part of these that make it easier to work with the system. So the goal is really, again, a consistent ORM implementation, right? So you don't have to worry about layer transitions and things that normally are very, very expensive in a state change system to retest all the different layers, all the different transitions. In this case, they're all coming from the same model, so you know that the the import layer is going to read the same JSON and expect the same structures and same model declarations that you sent to it from the front end. And all of that is done consistently because all of these things in green are generated from exactly the same model, and we know that they're consistent. It turns out the back end, these pieces, your JFE IO, which reads JSON, creates OR when I put a slash, I mean object relational mapping entities, which are also declared and generated by the system. So this goes obviously way beyond just generating the DDL, which is kind of what ORM or Norma has traditionally done, into generating a full stack application. So you'll notice there isn't a lot of blue again, right? When you get to the UI binding, yes, you still need to write your application, but we even make that binding layer much easier for you. So once you bind to the Angular layer, the changes are automatically applied to the back end. You have built-in services like a save button and undo redo button. So you just create a data store, and you automatically get these other features that are built into JFE that were requirements of the system, right? Rule validation, you get JSON import and export. The model declarations tell the system what it actually does, right? So those are your type declarations and link declarations. These green ones are for help in working with TypeScript. These are your main generated methods, right? So these two methods call these methods to the get closure gets the data, the import reads in state change data. So we'll go over the different parts of this layer in detail. I'm not going to go through in heavy detail all of the JavaScript fact engine and everything it does. Just a brief overview on how it's supposed to work. So the JFE library itself is a client framework that is designed for plugging models into its declarative system. So you provide models. The models are actually class factories, but it's JFE that creates the classes. The classes are really just used for typing. And your model is a list of these classes, right? If you keep the classes type name by convention, you can put functions and other information on there with lowercase as well, which we do. So properties are declared with the types. However, if you want to link the types together, that's actually done after all of the models are loaded. So types are separated into models, each of which have a short name associated with them. So to ensure that you can connect all types, that's done a bit later. ORM style objectification is required for ternary and higher, so you don't get confused going across the link. You basically have to go through a blob in the middle to figure out which of your endpoint roles you're mapping to. Of course, it's required or supported for binary as well, but it is not required. So you can do many-to-many collections without having an object in the middle that you have to navigate over. So once you have your model space types loaded, you create a fact base, which is your data. Fact bases were designed to be very easy to read. So you're using plain old JavaScript, right? Properties, collections for statements, etc. However, it was designed from day one to be difficult to write. You want the write to be synchronized, so you don't write directly to the data. You make a request to the fact base through a stock API of maybe a dozen API calls to make changes to the system. All links here are bidirectional, so if A can get to B, B can get back to A over the same relationship. That's very intentional. It's much easier in the system to do things like pivot your data and look from the top instead of the bottom than a traditional REST returning JSON system where you really have a hierarchical structure, and going backwards can be very, very difficult to do. So all of this data in the objects and all of these collections are synchronized by the fact base in response to the API changes. Any fact base can be changed with the API. You don't have to have a tracking mechanism on it, but if you want to do that, you create what's called an edit context. So the edit context is basically responsible for running transactions. A transaction is a function that is called, so you make user changes, and then after that there are responsive changes based on rules, etc., that fill out the system. So you have responses to add validation state. You can even throw if you want to. That's not normally done on a web. You don't want to be doing a lot of throwing on your client. And this also gives you a transaction object, right, called a state change, which is all of the changes that occurred during the transaction. State change objects are really our state, right? So this is what was added, this is what was deleted. This is not a step recording. It doesn't say change this property back. If you change a property and change it back, you have a null state in your state change. So state changes become an undo redo stack, right? You run a transaction, the edit context automatically records the changes, puts it on the undo stack. You can also have other change listeners, for example, an unsaved changes state. So when it comes time to save to the server, you have a cumulative state change that may cover multiple smaller undo items. So state changes can be merged, they can be rebased, you can roll back all your changes, get incremental changes from the server, roll forward all your changes, still have an undo stack that's consistent with the changes on the server. So that's the state change object. State change plays into everything, right? It plays in the rule engine, it plays on undo redo, it plays on save. State changes is what's sent to the back end to write to the database. It's really a fundamental part of the system to have a state change object. If you look at it in memory, it looks a lot just like a fact base. There's just a very small amount of additional annotation to tell you when objects are newly created or newly deleted. So I started this a long time ago, long before TypeScript was thought of. JFE is very much a JavaScript library. And even when you're using it in a TypeScript system, I minify it independently with the Google Closure compiler. You get a minified form that plugged in as a script into your TypeScript. That's not going to change. However, when you're dealing with your types, you really want the ease of use of a declarative system, or not declarative, but a fully typed system, right? So you want that for compiler checks, but you also want it for prompts, right? What comes next? You get these huge models, and you know it's very hard to remember the names of all the links and all the other things that go on. So the TypeScript interfaces allow you to do that. All right. However, the change system is made with API calls, right, which are string based. So here's the model name, here's the link name, here's the role name, changes to this role player, etc. Right? You don't get compiler checking on strings. So I've also written a change wrapper called a type fact base, which lets you attach to a fact base and then make type changes that are fully compiler checked. There's a small wrapper that supports this on the back end. It's very small, very lightweight, pass through, done with ES6 on ECMAScript 6 proxy objects. So it also reads the model like the rest of the JFE system and is able to translate the expected API calls into the back end. So that particular API is currently only produced by the Yorm web tool. It's not something I have in Norma Pro yet, and we'll discuss why that's moving more toward the web tool later. So of course interfaces in TypeScript look big. There's these huge files, but they have no effect on the runtime whatsoever, right? So it's a compile time mechanism. It does not influence the size of your final product that goes up to the web. It doesn't influence the runtime costs. It's just a helper mechanism, but it makes a huge difference in productivity when you're coding. So there's a reason most JavaScript developers and most libraries really are moving towards TypeScript, right? It's very hard to memorize these massive object models and know exactly what you need to type in at any given point. Of course, TypeScript is only part of the equation, right? We also want a modern UI layer. I currently have tools that are targeting Angular, although, I mean, looking at the Angular service layer, this could be made React very quickly as well. I think there are maybe 30 lines in the file that are actually Angular specific. So what's the point of a tracked wrapper class? Well, as I've said, on JFE, for example, you have an undo stack, right? So you don't really know if a change is coming based on a UI gesture or if it's coming because someone hit Control Z and the stack changed, right? Not your stack, but your data changed in response to an undo redo operation, which is actually not part of your local application editing, right? The changes come from external. So the wrapped objects in Angular track these changes, right? It takes a state change, says, what have you actually read from the Angular application? If there's an overlap, it notifies the component refreshes. So we can do very targeted changes using this mechanism. Each component is tracked separately and has its own mini state tracker inside of it, which is again intersected with any change. So the Angular interfaces that you use for generated by TypeScript are slightly different than the core JFE ones. One, they're writable, right? So you can actually write these collections. At some point you have to write. The ng model is something used in Angular that allows two-way data binding. So you read and write a property using these methods. So if something is functional, single valued, right, you're setting a single object or you're setting a property, you automatically get a transaction provided by the wrapper, which gives you, again, the undo redo stack, gives you all the rule validation, all the responsive stuff happens automatically in the UI. And then the changes are compared to what's been read, and the UI is updated automatically for you. Working with anything other than a bound UI in this day and age is really crazy because it saves so much time and so much code to have a change system for you. So there are several components in the JFE JavaScript Angular services that are written that are I consider standard. There's a save service, there's an undo redo button. Angular is a single page application, so you really don't leave the page, you just kind of refresh what's there. However, that means that you have pages that may share data with other pages that are, you're just moving around. So the first time you see a page, you may want to get data. There are services to do that. It's called the delay load service. And a few other things just for editor tracking what's active, and if I haven't left the editor, do I actually want to update the state? A few other services come in there. But basically, this gives you a very easy mechanism for producing bound UIs that directly modify the data. The only time you really need the component code, besides binding the initial object on the wrapped object, as soon as you have one wrapped object and you get another one, that will also be wrapped, right? The wrappers and trackers can stay in place. So if you need to do many-to-many relationships, there's really not a good way to do that automatically, so that is left up to the components to do that work. So this is of course on top of the TypeScript Angular integration. Angular is fully TypeScript now. So moving to the server side, the server doesn't really have a framework per se, it just has a bunch of generated code which runs on other frameworks. I'm not huge into let's do runtime engines that will read any model. So the generated code the model's integrated into the code generator, right? So the model is reflected in the classes in the code generator. That makes the system quite flexible, so theoretically you can pop your backends in and out and change databases and change and servers. In practice right now I have a PHP layer. That was just the first one that was requested for this. It shouldn't bother you too much because once you Dockerize it, it doesn't really matter what's running the container. So the PHP Doctrine 2 layer is doing the object relational mapping. It's a active record pattern. The .NET Core one would be entity framework objects, which I like to do as well. So the PHP is only doing the data. I'm leaving the Angular side to do the UI part of the application, and then you do some magic in the web config file that basically combines the two apps into one website. I'm using IIS Express as my main debug web server, but the Docker boilerplates I have are using Nginx to do the same thing. The web configs are slightly different, but once you get over that, it essentially works the same way. Okay, so Norma Pro generates the doctrine classes for you. These are an entity mapping onto the databases, of course, also generated by Norma, right? So you know that those are consistent between each other. So Doctrine 2 is an object relational mapping library. This actually gives you a way to generate databases that you don't have Norma support in. So I've never done, for example, a SQLite generator. You can actually generate a SQLite database from the produced Doctrine classes. Now there are a few things in the Norma DDL, like check constraints for absorb subtypes and this sort of thing that you're not going to get out of the relational mapping. But in a pinch, you can actually regenerate the databases from this class. So the point of this class is not to necessarily use it directly, although it is possible, but it does give you a way to write queries that are not specifically tied to a single database backend. You're still querying in terms of objects, not in terms of tables and columns, right? This is mostly there to support the I/O layer, which works very heavily with the, with the doctrine classes. The main code piece in the backend is the I/O layer. This is a lot of code, and it's difficult code. It's actually quite hard to write to a relational database. They're very picky, right? If you can't, for example, reference a table or a row in a table with an auto-generated identifier until that identifier is provided by the database. This is also true in relational mapping layers where you have to flush or send the data to the database, get the response, get the entity back. It now knows its identifier. Now you can reference it. So what this ends up with is a whole bunch of staging, right? So these objects need to be created and get their identifiers before these other objects are created so they can get their identifiers, which goes on and on and on. The ORM tool I looked at the code, has 7 stages, so 7 different layers of objects that need to be processed in order. The SSO, MVSE model has 8. And if you don't process them in that order, it doesn't work. So read goes one direction and write goes the other way. So the staging is only used for the mandatory pieces, right? I have to reference this other object. So if I'm going to create the object, I have to have a row that will actually insert into the database. So once you get all the rows inserted, now it goes through and gets all of the optional links between the databases, between the objects and the entities, and then flushes those at the end. So it does as little flushing as possible, but it still has to do multiple stages to get all of these pieces into the database. So the goal of this is to be able to take any model change, whether it's one small property change or import an entire model in one transaction, which is what the ORM tool does. It shouldn't matter, right? You want to be able to get that data, stage it, create the objects in the correct order that the database will accept them and push them in. So this is really a big piece of code and does, I'd say 95% of your backend work for you. That all of this used to have to be done individually. So the write method, or the import JSON, which pulls in a state change, is a much different mechanism that you would normally use for a web method, right? Most web methods, you have a very small data change. It's very specific, and you write a small amount of data to the database, right? Because doing this by hand, again, is very hard. But with the model, we're able to see those dependencies, predict how we can write to the database, and get that data in and get the changes in place. Occasionally, some constraints will bark when you're doing this. This is really not a JFE problem. It's a relational mapping problem. So they'll complain. For example, uniqueness constraints can complain when they're done at the row level instead of the end of the transaction. So if you have a system that does deferred constraints, occasionally I've had to move maybe 20 constraints in the whole time I've been doing this across 5 or 6 different large applications that cause problems. So just be aware of that if you get a uniqueness violation, that's why. So I wanted to show the basic code required. This is handwritten code. This has routing mechanisms on it, right? This is done with the PHP Symfony framework and is essentially boilerplate. So what this code does is gets the content, decodes it into data, and then we import that data into the import JSON function, which is 100% generated code. The true means return a string. So want the JSON string back, not the object form. And then we return that response. So the returned JSON here will be ID changes. So you take the local IDs that you've been using for however long you wanted to on the client, convert them into database identifiers, and then replace all history, including on undo stacks and other places, of the local identifiers with the database identifiers. That's not a lot of code. So this is the be-all, end-all of all the right methods you need to write any data to the system. So this is an example read method that gets data back out of the system. The boilerplate here is this line, these lines at the bottom. This gets your IO service. Expand closure essentially precompiles the query requests you make, and then the JSON gets the data. So you have a closure specification which says how you navigate between objects and what you want to write to the output. And then the root ideas are your starting points. So in this case, we want all. So this says give me all service types, all subservice types, etc. If I wanted to, for example, start with a service type and just get the subservice types for that service type, right, I could have additional links here. In this case, all of the links are implied by the identifier, so the only explicit link we have to make is right here, and hook the subservice up to its service containing, container service. Okay, so this again is very standard. This is actually JSON scrunched down for this slide. The JSON can be produced by a tool that we provide that you'll see in ORMweb and other places called the Query Builder. And the Query Builder tool validates the JSON for you based on the contents of the JFE model, which is what this maps to. These are not database names. These are names from the JFE system defined for this model. Although you have one write, normally you'll have multiple read methods depending on what kind of data you want back. And this is how you go about it. So you use the tool, you produce the JSON, you copy it as PHP, you paste it in here, and you run these lines, and then you say, well, what do I want to, how do I want to retrieve this? So data PUS service types. This one happens to have no arguments into it because it retrieves all of them. So in summary, extending an application stack based on ORM to more than the database makes a huge difference in productivity levels and the sophistication of the tool you can write with ORM. I really think that the traditional focus, which is very squarely on databases because ORM is so good at creating databases, has in some ways obfuscated the broader possibilities. People using a website don't really care what the database backend is. They just want to read and write their data. And having to view an application through the distorted mirror of tables and columns and stored procedures can really get in the way of being able to deal with your application. It also means that you're heavily dependent on one implementation detail, which is how the data is stored in the database. So I'm hoping that this has broadened that view a little bit to say, look, we really can create a full data stack up to and eventually including a lot of UI generation directly from an object role model.